to know what you knew. Best miss every time we start locking eyes up. Lost control. Oh, it's paradise with honesty, but I'm in the dead of the night. Let the darkness take control. Let the darkness take control. Darkness take control. May the darkness take control.
So linear momentum. Okay, I'll just go fast. I cannot go so detailed now. No time. So linear momentum, it is a product of, okay? Linear momentum can be defined as a product of mass into velocity, and it's a vector. Its SI unit is kilogram meter per second. Write down. Yes, now we cannot go that detail. You just write down now, linear momentum. Linear momentum can be defined as a product of mass and velocity. It is a vector. Its SI unit is kilogram meter per second. Next, law of conservation of linear momentum. Law of conservation of linear momentum. So remember, linear momentum actually tells us, we discussed this factor, I think. See, for a heavy train, okay, traveling very slowly. For example, a train bogie, 1000 kilogram mass, traveling with 0.01 velocity, will have around a 10 kilogram meter per second. At the same time, a small bullet, for example, 1 gram, that means 10 to the power minus 3. Or we can say 0.01 meter per kilogram. Okay, this is traveling with 1000 meter per second, will have same effect. That means one bogie of the train traveling 0.01 second, a small bullet of 0.01 kilogram traveling 1000 meter per second will have same effect. To stop this, we have to give a equal opposite force, same opposite force.
Yes,
Is
sir,
it
we
clear?
discussed this.
We discussed this one. Now, law of conservation of linear momentum. Law of conservation of linear momentum. Law of conservation of linear momentum. Say, for example, we are taking a container. For example, a box or in a room, closed room, whatever it is. In this room, say, for example, air molecules are moving, right? Suppose there is a closed room you are living. There is no AC, there is no exhaust fan, there is no fan, nothing, completely packed and sealed. Now we experience an air which is still air. We say, oh, where is still air? Air is not moving. But does it mean molecules are at rest?
No.
No.
Molecules
No,
are
sir.
making irregular random motion. Okay, for example, one molecule may be moving here. Its momentum may be m1, v1. Another molecule may be moving here. Its momentum is m2, v2. Another molecule moving here, m3, v3. Like that, if you calculate, see, this is m and vn. So total momentum, if you are taking, there is no net motion. The reason, if you are splitting it, is the vector addition. Okay, vector solution. This one we can split into 2 components. This one we can split into 2 components. There, here you can see this vector cancel. And this vector cancel. If you can add all these vectors of all the molecules within this container, we can see net value will come 0. Because this is an isolated system. That's what you feel, there is no net momentum in the total system. Clear? Now, if an exhaust fan is on, now a pull, air is being pulled this side. Now you can see all these molecules will move to that side. Okay, all these molecules will move to that side from this side. Now momentum, if you resolve, it won't get cancelled because all the components are to this particular place we are applying the force. So whenever a force is applying, there's a change in momentum taking place. If there is no external force acting onto this, that means net momentum remains constant. This is a basic idea. So the statement is total linear momentum of the particle interacting in an isolated system remains constant. This is a statement. Clear? As isolated system means no external force acting. Write down the statement. Law of conservation of linear momentum. The total linear momentum of the particles, interacting in an isolated system, bracket you write isolated system meaning no external force acting. I gave an example of external force. No AC, no fan, no exhaust fan, nothing. No forces exerting on these gases. Like that. So total linear momentum of the particle interacting in an isolated system, bracket, no external force acting, bracket closed, remains constant. Remains constant.
In an isolated
system remains constant. Now proof. We need a proof for it by second law of motion. By Newton's second law of motion. Proof by second law of motion. Proof by second law of motion. Look, let us imagine a system having the particle having linear momentum P1, P2, P3, P4, Pn, ... Okay, right now. Let us consider a system. Let us consider a system consists of particles. Let us consider a system consists of particles having their linear momentum, P1, P2, P3, ... Pn respectively. Then total linear momentum. These are all vector, okay? Vector addition only. Then total linear momentum P1 plus P2 plus P3 plus ... Pn is equal to P. Net linear momentum. We can say net linear momentum is P1 plus P2 plus P3 plus ... Pn is equal to P. What is Newton's second law? What is Newton's second law? Zaid immediately disappeared. Zaid, what is Newton's second law? Zaid.
That the
law of
unbalanced
conservation of
force.
momentum, right?
The force is directly proportional to rate of change of linear momentum, isn't it?
Yes, sir.
So here d by dt of x means what? Rate of change of position. This is called velocity. D by dt of velocity means acceleration, rate of change of velocity. Similarly, rate of change of linear momentum we can represent as d by dt of p. So we can say force is directly proportional to rate of change of linear momentum. This is the formula by Newton's second law. Bracket you can write this symbol d by dt indicating rate of change of linear momentum. This is the way you have to read it. Rate of change of linear momentum. Okay? Right now. F is directly proportional to d by dt of p. The meaning of this statement, d by dt means rate of change. So examples I have given: rate of change of position, rate of change of velocity, rate of change of linear momentum, like that. So F is directly proportional to rate of change of linear momentum. Okay. For an isolated system, For an isolated system, external force F is equal to 0. For an isolated system, external force is equal to 0. Therefore, d by dt of P is equal to 0. Look here. Rate of change of some value. For example, rate of change of x, you know, velocity. Rate of change of velocity, we know acceleration. But rate of change of a number 5, that is 0, right? Because
Yes,
rate
yes.
of change of 5, the value of 5 will not change with respect to time. Because 5 is a constant value, right? Am I right?
Yes, sir. Yes, sir.
Similarly, rate of change of pi value is 0 because pi is a constant. That means rate of change of p 0 means here p must be a constant. It means the value of p is not changing. Okay, right now. D by dt of p is equal to 0. It means p is constant. It means p is constant. It means p is constant. Therefore, p1 plus p2 plus p3 plus dot dot pn is equal to a constant. This is what law says. Total net linear momentum of the particle interacting in a system remains constant. Clear?
Yes, sir.
Next, law of conservation of linear momentum by third law. Law of conservation of...
Sir, sir, what was the last line?
That proves linear momentum is conserved. Previous one. Next, law of conservation of linear momentum. Law of conservation of linear momentum by third law, Newton's third law. By Newton's third law. Law of conservation of linear momentum by Newton's third law. What is Newton's third law, Fahim?
For
Every action has equal and opposite.
For every action, there is an equal and opposite reaction. So this is what we have to bring the idea here. For that, right, you're right. Let us consider two objects of masses. Let us consider two objects of masses. M1 and M2. M1 and M2. Traveling with initial velocities U1 and U2. Traveling with initial velocities U1 and U2. Bracket, you're right. U1 is greater than U2. Traveling with initial velocities U1 and U2. Bracket, you're right. U1 is greater than U2. Otherwise, they won't collide. When they collide each other, this is A, this is B. When they collide each other, they exert force each other. By Newton's third law, they exert force each other. They exert force each other. That means, see, this is a diagram. A exerting a force on B. That is force acting on B by A. Okay, only diagram you mark now. Force acting on B by A. Now the momentum of B will change. Momentum of B will change now. Now B is M2. Its velocity become V2. Similarly, momentum of M1 also will change because it gets a reaction, equal reaction, right? That is M1, this become V1, and think they travel again in the same direction. Anyway, it can travel. I told you this example. On a skating wheel, A heavy person, okay, very heavy person standing here, a small boy go and push him with a 100 Newton force. He will also move, this boy also will move. They will get equivalent opposite reaction. So acceleration of this man depends on action by his mass, reaction on this boy. Okay, that is 100 Newton. That all we discussed before. Equivalent opposite reaction will come. Do you remember that?
Yes, sir.
Yes, sir.
Then there is a change in momentum. So until where you have written, let us consider an object of mass m1 having initial velocity u1 and m2 having initial velocity u2.
Yes.
At an instant, they collide each other. Have you written that part?
Yes.
Let delta t is the time of collision. Let delta t is the time duration of collision. Let delta t is the time duration of collision. Then their final velocities are v1 and v2 respectively. Then their final velocities are v1 and v2 respectively. Then force acting on the object B by the object A. Force acting on the object B by the object A. Bracket you write action. FBA, action. That is FBA. FBA produce change in momentum of B. Is the force acting on B by A, that is action, that will produce a change in momentum in B. What is the final velocity of B? M2 V2. B has this momentum finally, initial momentum, M2 U2.
Sir, your voice is not clear, sir.
Yes.
Then the force acting on the object B by the object A. During collision, force acting on the object B by the object A. Bracket you write action. Then write FBA. is equal to rate of change of linear momentum. Final momentum minus initial momentum divided by time of collision. So M2V2 minus M2U2 divided by delta T. Have you written?
So lagging.
Yes, sir.
Sir, that
again
is
your voice is lagging.
M2A2.
Can you say again?
M2V2, it's on the board, right? I'm writing it on the board. FBA is equal to M2V2 minus M2U2 divided by delta T.
Sir, I think it's the net issue that you're lagging.
Net issue. Just look at the notes now. M2V2 and M2U2 by delta T. Have written?
Yes, sir.
Then by Newton's third law, the object B gives a reaction to A. Object B gives a reaction to A. That is mark F, A by B. Force acting on A by B. This is reaction. Then momentum of A will change. M1V1 minus M1U1 divided by delta T. This reaction. That is minus. By Newton's third law, minus will come. Equivalent opposite reaction. Okay. By Newton's third law, action is equal to minus reaction. What is action? FBA. What that already know. FBA is what? M2V2.
Your voice.
M2 divided by delta T is equal to minus M1 V1 minus M1 U1 by delta T. Now delta T cancel. M2 V2 minus M2 U2 is equal to minus M1 V1 plus M1 U1. Then bring one side to other side. Then we can write here. We can't do anything. It's a net issue. We can't do anything. You just copy down. Now here M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. M1 U1 plus this goes here. M2 V2, this will come here. So here, total linear momentum before collision is equal to total linear momentum after collision. So this is also Newton's law of conservation of momentum. Two ways they will ask you to prove. This is studied in 9th standard.
Yes, sir. The derivation.
So this one.
Sir, can you repeat the last sentence? Last sentence.
Total linear momentum before collision is equal to total linear momentum after collision. Total linear momentum before collision is equal to total linear momentum after collision. Okay.
So we have to rejoin.
No, only 40. This is only 40 minutes. Class will be over by 12:20. That's all. Then next I have a next period. This is what I'm not going to.
Yes.
Now just come one more time. 5 minutes left. Start once again. Okay. One more time we come. 5 minutes less because every 5 minutes we need. Come fast. Join fast.